Okay, this is chapter 12. Let's look at chapter 12. Our first question that we have today is question number 2. A sailor strikes the side of his ship just below the waterline. He hears the echo of the sound reflected from the ocean floor directly below 2.5 seconds later. How deep is the ocean at this point? Assuming the speed of the sound is seawater is 1,560 meters per second. Use table 12-1 and does not vary significantly with depth. So we're looking at 12-1. There's chapter 11. Let's get to chapter 12-1, see what we're dealing with. And in 12-1, a little too far still. Here we are. 12-1 looks like we're doing the characteristics of some sounds. And I see that we have velocity, speed of sound. There's our speed of sound. Loudness, auditory, and we have some example problems. 12-2 in this book. And 12-2, it tells me that it looks like we're dealing with V is equal to D over T, as I can see right here. V is equal to D over T. Okay, so let's think about that as a possibility to help us with our answers, even before we attack this problem. So to begin with, in question number 2, so we got what's going on is we have it's going to be going down. The echo sound is going to be going down, hitting the ocean floor, and then bouncing back up. Looking at that, I probably can use my equation V is equal to D over T, just as I saw in that previous example. But in this case, I think we're looking for the distance. Okay, so we're looking for the distance. And so the distance is going to equal to V times T if I rearrange this equation. And so in this case, I'm going to have 1,560 meters per second. And then I'm going to do that in a time frame of 1.25 seconds. I'm going to multiply these two together, and I'm going to get an answer, 1,950 meters. And that would be my answer for number 2. Perfect. All right, number 3. It's pretty easy. Of course, it's only a little 1 there. So calculate the wavelength in the air at 20 degrees C for sound in the maximum range of human hearing, 20 hertz, to 20,000 hertz. What is the wavelength of a 10 multi-hertz ultrasonic wave? Ooh, okay. So we have 2 parts to this. First part is we got to calculate 3A. And in 3A, we're just going to look at our formula where we said that the velocity, again, is equal to the wavelength times the frequency. Oops, times the frequency, not divided by. So the wavelength is the wavelength times the frequency. And so I want to look for, in this case, I'm looking for the wavelength. So we got the wavelength. That's going to be equal to V over F. Okay, and so what kind of information do we have? As we look at the problem, we see we have 343 meters per second. That's our velocity in this question, which is the speed of sound. Meters per second. Our frequency is 20 hertz. And in this case, I will get about 17 meters. 17 meters. Okay, so what if we rank this up a little bit to the 20 kilohertz? That we need to do. And so if we did that, we'd have the wavelength at 20 kilohertz is going to be equal to, again, V over F. And so we got 343 meters per second over a frequency of 2.0 times 10 to the 4th hertz. Now that we're doing a little bit more. And in that case, this one's going to be 1.7 times 10 to the -2 meters. And so we have an audio range of 17 meters to 17 centimeters, in other words. So we go from 17 centimeters to 17 meters, and that would be my answer. Okay. And so our next question is number 4. Our homework. An ocean fishing boat is drifting just above a school of tuna on a foggy day. Without warning, an engine backfire occurs on another boat, 1 kilogram away. How much time elapses before the backfire is heard by the fish and by the fishermen? And so here's our little picture in this problem. So we have a nice little picture of the, what's happening. We have 1 kilometer here. We have the boats, the difference, and the fish right below. And so we're going to use this figure to be able to solve this problem number 4. A little bit trickier than our previous problem. So in the first part, in A, For the fish, the speed of the sound in the seawater, we got to find that distance and the time that's going to be in that time frame. So again, we're going to use v is equal to d over t, distance over time. And so we're going to look at this and we're going to try to find that time frame first of all. And so we look at the time frame is going to be distance over velocity, and we know the distance in this case is going to be 1.0 times 10 to the 3 meters, or 1,000 meters, and a velocity of 1,560 meters per second. Okay, and so we're going to end up getting a time of 0.64 seconds for the first part of A. And so, so before the backfire is heard by the fishermen, so we're looking for that time frame that it's going to be done, 1 kilogram, and then the next thing we need to do is to look at by the fishermen. So, okay. Any other information we need? I don't think so. Okay. So in B, we are going to see that we're going to look at the speed of the sound in the air. So we're going to look at the speed of the sound in the air, distance over v times t again, or same kind of formula. Again, we're looking for the time is going to be equal to the distance over the velocity. And in this case, our distance is going to be 1.0 times 10 to the 3 meters. Our velocity is 343 meters per second. And that's going to give us a time frame of 2.9 seconds. Okay. All right. Okay. And the next thing, and we're just looking at the distance. If you're looking for your velocities, you got to go back into the book to find the velocities going through different mediums. This is going through air. This is how the speed goes through water. So this is why the fish will hear that velocity much faster than the fisherman, because the velocity is traveling the speed of sound here, where this is traveling the speed of sound through water. And that's just something that you would have to look up in order to answer this question, which could be a point of confusion for some people. All right. Now we got a question number 8. So we're going to go deeper. In question number 8, it says, what is the intensity of sound at the pain level of 120 decibels compared to that of a whisper at 20 decibels? Okay, so we're doing 12-2, so it's the kind of stuff that's in 12-2 first. It's always helpful to look at the section. It kind of helps you determine some of the equations, and you can see right here, here's an equation dealing with decimal levels. It's 10 log of the intensity and over the initial intensity, okay? So more than likely, since this is an easy question, that's probably where we're going to start. We have some example problems of this. We can see that equation being used. We've got some more difficult one problems here. Maybe that might be used later. And then 12-3. So let's see what's happening in question number 8. In question number 8, okay, we got the decimal levels that we're looking for. And so we know that the pain level is 120 decibels. And we know that we saw that our equation is going to be the 10 log of the intensity at that 120 decibels minus our initial intensity. Okay, so we're going to look at the difference between these guys. And so I'm going to say that I'm looking at the intensity at 120 is going to be equal to 10 to the 12th times the initial intensity. Okay, so we know that we have 10 to the 12th, which this is going to equal 10 to the 12th times 1.0 times 10 to the negative 12 watts per meter squared, which in the end will give us a decimal reading or intensity reading of 1.0 watts per meter squared for that first part. Now at 20 decibels, and this is going to be what it's going for that first part. And for the next part, we're looking at 20 decibels at the whisper level. And we do the same thing, 20 log I of 120, I over 0. And then we're going to take the intensity at the 20, what's going to be our intensity, 10 to the 2 this time, times the initial intensity. And so in this case, we got 10 to the 2. Our initial intensity we're going to use is 1.0 times 10 to the negative 12. Oops, 12. That's watts per meter squared. And so now we can solve just as we did before for our intensity. And it's going to be 1.0 times 10 to the negative 10 watts per meter squared for that one. Okay, and so that is our answer for number 8. So if you look at this one, we can just and then you just got to make a comparison of these two, and you can see that the pain level is 10 to the 10 times more intense here than it is here. Okay, as you compare those two answers. All right, our next one is 10. Getting close to the end here. Question 10. If two firecrackers produce a sound level of 95 decibels when fired simultaneously at a certain place, what will be the sound level if only one is exploded? Hit at intensities, not decimal levels. Oh, okay. So number 10, we're going to be dealing more with kind of almost like a beats kind of question. And so we're going to look at, we look at the sound level. It's going from 95 decibels. If two firecrackers just sound level of 95 when fire simultaneously at a certain place, what will be the sound level if only one is exploded? All right, so if we look at the, we're missing something, aren't we? What are we missing? Add intensity to produce the sound level fire at a certain place. What will be the sound level if only one is exploded? All right, so the way we start this problem is we start noticing that we have the decimal level being about 95 decibels. If you look at the example problem, let's see, maybe we have, oh, here we go. If you look at the example problem, you can see that the intensity is going to go down by about 3 each decimal each time that you do this. And so that's going to be kind of important because we're dealing with this section of sound intensity on street sound levels and decimals. Is where you're going to find this information. And you're going to see that the decimal level goes down about 3 each and every time. And so I'm going to use that value and say, all right, the decimal level is about 95 decimals. And I can say, you know, if we see that the sound level decreases of 3 decimals to a having of intensity, thus the sound level for one firecracker is going to be 95 minus 3 decimals, which is going to get us a decimal level of about 92 decimals. And that's all we had to do for 10. Number 11. For example 12.4, we see that a sound level decreases of 3 decibels to having, we got to read our question before I start answering that. A person standing on a certain distance from an airplane with 4 equally noisy jet engines is expressing a sound level bordering on pain of 120 decibels. What sound level would this person experience if the captain shut down all but one engine? Add intensity, not decimals again. So, all right, so we're going to do the same kind of idea. You know, we'll use the example 12.4 again with the minus 3 decimals that we have. So if we'll be cut in half, and the sound level, we're going to start off as 117 decimals. We're going to subtract 3 decimals by taking that out right away. And we'll find out that this time we are going to have, instead of 117 decimals, you're going to have 114 decimals by cutting that in half. Coolio. And that's all that we have for homework.